In this video, we are going to have a better look at matrix exponentiation. First, we have to look at binary exponentiation. Let's say we have two square matrices of size k. How do we exactly multiply these two by each other? For each element in the answer, we need to perform a pairwise multiplication in the former matrices. Given that the resulting matrix has k squared elements, we need to perform k cubed operations. Let's say we want to calculate the nth power of matrix M. The naive approach would be just to simply multiply these matrices by each other. We are going to have n-1 multiplications. Each multiplication costs k to the power of 3 operations. So overall, we'll be having O(n) times k to the power of 3. A better way to do this would be to use a divide and conquer approach. If the power n is even, we can simply rewrite it as the square of its square root. Otherwise, we can simply multiply its previous even power by m. For example, when calculating m to the power of 13, we can factor out an m, halve the power once more, and once again factor out an m, and then halve the power for the last time. This method heavily reduces the number of multiplications needed. In fact, we'd only need a logarithmic amount of operations. Now our time complexity is k cubed log of n. You can view this method as simply writing n as its binary representation and doing multiplications for each 1 bit. So for example, here we are doing 3 multiplications and doing is squaring in 0 bits. So here for 13 we just do squaring once. We'll do 1 operation for each bit, so the total number of operations is equal to log of n in base 2. We can use this method to effectively compute the Fibonacci numbers. The Fibonacci sequence is a recursive sequence in which each term is defined by its 2 previous terms. Trying to extend this sequence recursively isn't always the best option. For example, let's calculate the 6th Fibonacci number. If we draw the recursion tree of our calculations, we can see that a lot of nodes are redundant and shouldn't be computed twice. These nodes are the nodes in orange. A better way to approach this problem is using dynamic programming. We can store the results of our previous calculations in a DP table and use them to calculate the new numbers in our sequence. This is much faster because it only needs O(n) operations. But what if n was really huge, like as big as a quintillion or 10 to the power of 18? Then our dynamic programming table would need to be huge as well because it's proportional to n. So let's see how long would this method actually take. Modern computers do 1 billion operations in 1 second, and we'd need a quintillion operations, which is around 11,000 days. That's a lot of time. A much faster solution would be to use matrix exponentiation. We can reformulate the Fibonacci sequence as a matrix, then use induction to support our calculations. We start with our base case, call it matrix A. In our inductive step, we want to prove that multiplying A by itself would actually push it in the Fibonacci sequence. We can see that this holds true by algebraically writing down the calculation since the matrix is small enough. This method especially shines in huge numbers like quintillion. We knew that our dynamic programming approach was really slow and took almost 11,000 days. Now this new approach, which uses binary exponentiation, takes under a second. How wonderful is that? What makes this method truly special is that it can be used for any form of linear recurrence. They can be viewed as sequences which are made up of two components, a base case and some coefficients. Our goal is to find the nth term where n can be arbitrarily large. Just like the Fibonacci sequence, we'll start by building a transformation matrix to use it to advance our base case one step further. This matrix is made up of some shifting rows to keep our base cases intact. The other main component is a recurrence row which calculates the next element of the sequence. Putting this all together, we only need to apply this transformation matrix to our base matrix n-1 times in order to advance it to the s of n, which gives us the nth term. By using binary exponentiation in this method, we only need log n matrix multiplications, with each multiplication taking k cubed time.